think you have been enlightened by the talk of Professor George Fitzgerald Smoot, and I hope you can field as many questions as possible. I think Professor George Fitzgerald Smoot has a lot of slides that can answer all your questions. He seems to be he seems to be predicting what are the questions that we're going to ask. Okay, so I think there's a young guy here who just raised his hand. Want to give a so we give him the opportunity to ask a question.
My question is, I believe that there is a theory that postulates that a form of energy known as dark energy is causing the inflation of the universe to accelerate. However, we are not really sure what this dark energy is. I believe that it may be possible that this dark energy stuff does not exist, and that the acceleration of the universe could actually be decreasing. It is possible that, could it be possible that there are areas in the universe that are less dense than others, so as light traveling from, say, an event that occurs in an area where the expansion is decelerating due to the amount of matter in that area, proceeding into an area where the density of matter is less dense than in other areas, would make it look as if the expansion of the universe is actually accelerating. Would that be possible, as in a less dense area, the deceleration of the expansion of the universe would be less?
So this is a good question, because we've only known about the acceleration of the universe for just about 10 years. He was already born. So he's going to be old compared to our knowledge, right? I mean, so this is a young man's field, so it's good. You got to be paying attention though. And so for a while, many people didn't take it seriously. And then there are many people who say it could be modified gravity, or some people saying, well, wait a minute, we could have a situation where we're fooled into thinking that the universe is accelerating because, in fact, we live in a bubble in which the density is less than the average density in the rest of the universe. And if you live in a bubble, the matter in you is being pulled out more. And in terms of expansion, you have gravity, attractive part of gravity pulling you in, and you have the expansion of the universe pulling you out. And if you have less material where you are, you will be pulled out faster. Your bubble will get bigger. That's why one of the ways those voids appear is because the universe is expanding. The places where there's slightly more material, that doesn't expand as quick, so it stays denser. But the places where there's less material expands more quickly and spreads out, as well as having its material attracted out to the areas where it's more dense. And so people have tried to come up with theories in which we live in a special place. It turns out when you put the numbers in, you have to live in a special place in the universe. You have to live very near the center of a void, which has to have, right around us, close to the average amount of material, but not exactly the average amount of material. And then further out, right, sort of halfway out the universe, halfway out the invisible universe, a void which is much, in the sense that it's much less dense, so that it's expanding more rapidly than the rest of the universe on the average, so to say. And then go to the more normal outside. And so then the question is, how likely is it to have something that large? And then how likely is it we're that close to the center of it? And the reason for that is we do some very careful measurements now. I figured you were going to ask me about that, so I have some slides about how you actually measure that the universe is accelerating. That is, how do you measure that things are moving apart faster at a faster rate now than they were in the past? And but we have measurements where we go and use standard candles or standard rulers, standard objects out into space, and we either by the angular distance or by the luminosity distance, how much the light has fallen off, we're able then to tell how far away they are. And by measuring the redshift, we can tell how much the universe is expanded. So we can actually make a plot of the expansion rate of the universe versus time by just measuring distance, divided by the speed of light, and by measuring how much light is stretched from the time the light started to us till the time it got to us. And so you can measure the trajectory of the universe very well. We've been working on that, and we've made a fair amount of progress. And one of the best tools we have, when the discovery is made, is you use a certain type of supernova, which is a very standard brightness. So type 1A supernova. It is characterized as being thought to be from white dwarf stars. They're carbon nitrogen stars, and they accrete material from their neighboring stars. And when they reach to a critical limit, they flash and make a supernova. And so the physics is very standardized. The threshold is set by fundamental principles. So you get a very specialized amount, and it's a very simple correction. It takes something just a few percent variation and sends it down even more, down to the 1% level. So you can use this as a very good distance indicator and a very good time indicator of what's going on in the universe, and make these plots. And you've measured them mostly from the northern hemisphere, so you could say, well, it looks different somewhere else. But there are some measurements from the southern hemisphere, because one of the groups has one of its leaders in Australia and gets also time in Australia. And we've also been using cosmologists have also been using the Hubble Space Telescope to look for more distant ones. And so when you actually look very carefully at these, you find you are in this situation where you must be relatively near the center of a bubble, right? And you can look far enough at the Hubble Space Telescope at the supernova. You can go back to a time when the universe was not accelerating. You can actually see the universe is slowing down, and then you can see it start to speed up by measuring these curves. We haven't got a lot of data points, but we have some. And so we actually have evidence that you would have to have, you'd have to be in this special bubble that's near the center of the special bubble, and then it has to go up the normal further out there. So it's a good question, and people have asked that question, but now by observation and care, we're able to rule out it being a random sort of thing. And there are even people who've tried to publish papers saying solving general relativity comes out there where there's arguments about whether in a spherically symmetric case it's possible or not. But what really matters is in the end what the observations tell you. And then you'll eventually get the equations right. You'll solve the problem properly and get the equations right. So one of the things that people worry about is, well, maybe general relativity is not correct. We know it has a concept for quantum mechanics. Maybe there's some other corrections that have to be made. And maybe there's an extra term in general relativity that could cause this accelerating expansion. And in general relativity, it's a very simple concept. It says, on this side of the equation, it says the curvature of space. On this side of the equation, it says the contents of space, and there's a proportionality constant. It just says the curvature of space-time is proportional to the contents of space-time. And the other side of that equation is, if you curve space-time, then that tells the matter and energy how to move, right? So it's the action and reaction principle still holds true. If something can act on something, it gets reacted back upon and moved away. So, but you could modify those equations. Einstein actually tried to. He tried to add a constant to it. This cosmological constant could, if Einstein were correct, the cosmological constant would eventually lead to accelerating expansion if it were a positive quantity. Right? The only problem is we don't have a physics motivation for what value it should be. But the other thing you can do is take the cosmological constant from the curvature side of the equation and you put it on the other side of the equation, and now it becomes a new thing. Either the vacuum energy, if it's truly a constant, something that's just associated with space-time itself and it's fixed forever, or it could be a totally new kind of thing, the new force field or a new kind of energy or force, and then it could change over time. It could go through phase transitions just like water can turn to ice, and then it could change from being repulsive to being attractive. And it's important to us to try and figure out what that is because it predicts the future, but it also tells us about what's going on because we really think that it should make sense and there should be more than one way to see how it goes.
Okay. Any questions? Further questions? Yeah. Well, yeah. I think the audience needs to hear. It's not a big audience, which they share. Okay.
Thank you. Thank you, Professor Smoot. I would like to ask you, let's say, one of the most fundamental questions the human beings are occupied with. It's a metaphysical question, it's not a physical one. When you were showing to us the form of the universe and also how old the universe was, you mentioned 13.7 billion years.
Yes.
then I think everybody of us asks, everybody who is a religious person, what happened before 13.7 billion years? First of all, I mean, this is the time questions of the universe. And secondly, showing to us the form, this oval, even speaking about billions and billions of miles, if I would put it in a distance criterion. What is beyond this universe? I mean, where are the limits? Are there any limits, or is the universe limitless? I mean, you as a Nobel laureate and your learned colleagues, are you occupied with this question? Do you study this question? Does this come up in universities and faculties of science?
It comes up in universities. It comes up even more often in cosmology conferences. And in fact, there will be a cosmology conference sponsored by the Vatican at the end of November, beginning of December, to address some of these very questions. And we, as cosmologists, we think it's our grand goal to be able to explain everything, the entire universe, and everything in it. And it's physical. It's everything. And so the question about how big the universe is a question that's been around for quite some time, and has been formulated carefully mathematically since 1915, when Einstein gave us equations that allowed us to realize space was curved. And it could be curved closed like a sphere, or a four-dimensional sphere, or a three-dimensional sphere. Or it could be open like a saddle, or a funnel. It just keeps spreading. It's got to have something. Or it could be flat, and if it were flat, it would be simply infinite. If it's a saddle shape or a funnel shape, it would be infinite also. But if it's closed, it will be finite in volume, just like a sphere is finite in area. Right? So it's hard for people to think in three and four dimensional, about three-dimensional space and four-dimensional, embedded in four-dimensional space. It's difficult for people. But if you take and think about two-dimensional surfaces, you're used to thinking about them, you can put them in three-dimensional space, embed them and so think about a case where the universe is possibly curved and it closes. So the natural shape is a sphere. You can then add one more dimensions and it'll be a four-dimensional sphere. And in the case of a sphere that's a perfect sphere, there is no place that's special and no edge. Right? It is a closed finite surface, has a finite area, 4 pi r squared, but there is no place that's special on it. Every place is equivalent, and there's no edge that you will fall off of. Now, because we've embedded in something you're familiar with, a three-dimensional space, you can think of, if you weren't trapped in 2 dimensions, you can think of going inside the sphere or outside the sphere, and you might ask what's on either side of the sphere. But the universe, you can write simply down an equation you can go to 4 dimensions, x, y, z, and add w or something like that, and just say the 4-dimensional sphere is defined by this thing which is x squared plus y squared plus z squared plus w squared is equal to r, and solve all equations for that. And then you can eliminate the w from it, so you have just the equations in 3 variables, because that's required for all the points. And you can derive all the properties that you want to with very simple mathematics. And you would never know if you lived in that closed or open space unless you make very careful measurements. And so Gauss is the one that defined that, which is if you look at the sum of the angles in a triangle, if it's exactly 180 degrees, you live in a flat space. And if you live in a positively curved space, it will be more than 180 degrees in a negatively curved space, as an open space. It'll be slightly less than 180 degrees. So we do measurements like that, and we see that the universe is very close to flat. Within our errors, it's flat. And we know that if you take the surface of the universe, as far as we can see, 14 billion light years in any direction, that if you fit a tangent sphere to that, the radius of that sphere that will fit to that is certainly larger than 10 times the 14 billion years. It's more than 150 billion, light years. So we're a very flat surface. And in fact, there's plenty of reasons to expect, since the average variations are at 1 part in 100,000, that the radius of curvature is at least on that scale. That is sort of a statistical fluctuation. And that's just happens to be how big we see, and it could be slightly positive or negative, but if we were able to continue to improve our measurements from the current now 1% level, slightly better than the percent level, so that turns out there's a flatness, but that goes as R squared, so it's only gives you a factor 10. That if we were able to continue to improve, we would expect the curvature to be at least below part 900,000. Right? That it'll be at least 100 times and probably thousands of times bigger than what we can see. So the universe is very flat, and in the case that on average, on a very large scale, it's flat, the universe could be infinite. So even though I said all 100 billion galaxies that we see now and the space that contains them was all once smaller than an atom, there still could have been an infinitely large universe, right? And the question of in or out doesn't matter. In the case that we're in a closed universe, it could have a finite volume. It would still be very big, much bigger than what we can probably see. There, then you ask the question about in or out. That's a little tricky. But you can think of the simple model, again, back to 2 dimensions of a sphere. When the universe is very small, the sphere is very young, it's very small, and as time goes on, it expands outward, right? And so in that case, when you ask about what's inside the sphere, it's the past, and what's outside the sphere, it's the future. That's because you're trapped as a human being, we are trapped in 4 dimensions, that is space plus time, and we have models of the universe in which the forces, the 3 of the 4 forces, are trapped in 3 spatial dimensions and 1 time dimension. But gravity, which we used to think of as a weak force, actually can go out to many more dimensions. It is equally strong, but it's diluted, right? Just like if you have a light bulb, right, and you channel its light in a beam, it stays bright. But if you spread its light in all directions, it becomes much weaker. Gravity can be much weaker, even though it was as strong to begin with, because it's spread out into more dimensions. And so it becomes important to us now to understand, see, one of the questions that we're motivated by, but we don't have any evidence that exists. We have plenty of evidence now that there are only 4 large dimensions, 3 space dimensions and 1 time dimension. But it could be that we're fooling ourselves. There could well be some extra large dimensions, and we're trapped. Like there's a book called Flatland, famous book called Flatland, where you imagine a set of beings that are trapped to live in 2 dimensions, right? And they're trapped on that. It's just like bugs being trapped on the surface of the earth. They can't fly. They must stand there. We think that we could be trapped in 3 dimensions. We call that a membrane. And then you can have spaces. You can have 2 universes that were, 3 dimensions of space, and they're physically almost touching, and you wouldn't be able to tell because they're just slightly separated in the 4th dimension, in the 4th spatial dimension, and you wouldn't know. And those are called brane theories, the brane theories. And one of the models of how the universe began was there was a brane, anti-brane, and they collided, and their energy. They got turned into pure energy, and the energy got transferred to another brane that looked like the beginning of the universe because it was very hot and very dense, because you got particles. You turn some of the energy into particles, and it looks very hot and very dense. So there's a theory that says that. It turns out it doesn't agree very well with the observations. It's the wrong kind of spectrum of observations. So even though it's kind of a cute theory, it's not probably right. That's where we are. We used to not be able to say, people wouldn't even make up theories like that because there wasn't any chance, there was no motivation to do it. Now we rule them out, right? There's many theories that are ruled out already, and people are trying to come up with other schemes. And one of the reasons that people started thinking about extra dimensions is it's one of the few ways you can reconcile the theory of gravity with quantum mechanics, which is a basic theory of the last, probably the most basic theory of the last century, even though we're very impressed by general relativity and relativity in general. It's only part of the story, and quantum mechanics probably tells us much more. It tells us how digital the world is and how things fit together, and how our simple classical way of looking at things is only a very small part of the story. And so most physicists, if you ask them which theory is going to break down, general relativity or quantum mechanics, they would say it's more likely it's going to be general relativity than quantum mechanics. We'll see. So string theory was an attempt to reconcile them and prevent the catastrophe from happening by not allowing things to get so tiny that the conflict would be insurmountable.
Okay. Anyone got questions? Yes, Siti Jamil.
You said that the measurements made concluded that the universe is flat. So I would like to know what kind of measurements we're talking about, and how do you measure the curvature of the universe? Is it based on astronomical observations?
Yeah. Okay, so it turns out that it's a study of the cosmic microwave background that gives us the most precise measurement of that the geometry of the universe is flat, and it even tells us something about the topology of the universe. So one of the things that could happen is that the universe, you could think of it, if you go to 2 dimensions like this sheet of paper, you could think this could go on forever, right? But it's also possible that you can make a universe that's a cylinder. Just take a piece of paper and wrap it around. It's still a flat universe. You can cut it. You can still lay it flat, so there's no curvature. It's a flat. The geometry is flat, but the topology is not. The topology is connected. So it's a difference between topology and geometry. And so it is possible for the universe to have complicated topology, like a coffee cup has a handle and so on. The universe could have a more complicated topology, in which case light will travel around in funny loops because light has to go in as straight a line as it can, and will travel around in funny loops, and you will see the effect. So when you can see out very, very far, and you can see very large-scale motions, large-scale variations across the sky, like the microwave ones I showed you, you can tell how big it is. So I used to have a picture that I would show, which is a picture of a cafe that looked like a 3-dimensional cafe. It was a table, 2 chairs, a little cafe table, 2 chairs, and a vase with a rose in it, right? And then it repeated in a cube in all directions, right? And the question was, is it a 3-dimensional cafe, or are there windows on is it a cube with mirrors instead of windows, right, between the things? Right? And how can you figure that out? Well, the answer is look at the carpet. If the carpet has a ripple in it, it goes across several tables. Clearly, it's not mirrors; it's clearly tables, right? And so we have that in the universe. So we can tell about the size of the universe. And so one of my students, she was actually a Brazilian student, Angelica de Oliveira Costa. That was her PhD thesis, was to analyze the data looking to see. And there, in the simple models, we were able to show that the universe is at least 3/4 as large as the 14 billion light years. That is, we see structures, we see waves out across the universe that large. Since then, people have done many studies where they look for more complicated patterns, because if you can imagine the universe as a cube, you can take this edge and put it to that edge. That's pretty straightforward. But somebody could be wicked, and they can take this edge and put it on that edge. Right? And then your view is complicated, right? Because then you have to reconstruct this guy's up, the next guy's upside down, or whatever it is. And then the rows should be aging, right? Because light takes a long time to travel. So there are very many patterns you could put together, the basic patterns, and you could start with cubes, and you can have hexagons. So it turns out the topology of the universe could be very complicated. And because of quantum mechanics, you kind of expect that maybe it is. But if you have this inflating acceleration period, it can take such a small region so big that it pushes the topology way beyond where you can ever see. It's very simple. So that's the first thing is you define the topology, right? But you can also do experiments to see the geometry. I'm trying to see now if I have a slide I can show you. I know I have a slide I can show you, just finding it. Here it is. Not too far. Here we go. Okay. So now I'm going to explain to you how I can determine the geometry of the universe. All I have to do is have a standard ruler. Right? So you know if you have a ruler stick that you put on the ground and it's 2 meters high, typically what surveyors do, and they go far away as a surveyor and measure the angle from the top of the 2 meter stick to the bottom of the 2 meter stick. I can tell how far away it is by just measuring that angle. Because if I know side, or I know angle and side, I can measure distance. If I know this side and the angle subtended by it, and it's an equilateral isosceles triangle, it's a symbol. I can draw the middle one, the 1 meter, right? It's half that angle. I can use the sine of the angle, and I know exactly the distance. So it's easy trigonometry to do that, as long as I live in Euclidean geometry. But what happens if I live in a geometry that's not Euclidean? So let's consider the case of being trapped on the Earth, and I'm at the equator, near the equator, and I start two lines parallel from the equator, and I propagate them along the Earth in a straight line. They come together at the pole, right? So 90 degrees, plus a little angle at the pole, right? So if I have a positively curved surface, the sum of the angles is greater than 180 degrees. And if I project backwards, right, the angles when they curve, if I project them back using Euclidean space, the angle will appear to be, the object will appear to be bigger than it is, right? This object, when it comes in, will look to me to be bigger, right? And likewise, if I have a universe that's open, right? So imagine a funnel. So it starts, it's just a round cylinder, but it funnels out and it spreads out. I start parallel lines down here, and they will fan out. Right? So the light coming back from an object far away will come together and converge more. So that will be the case here, and when I extrapolate back, it looks smaller. Right? So all I have to do is have some standard size object, something I know what the size is, and look and see how big an angle it depends on the sky. If the universe is positively curved, I'll predict the pattern from my computer calculations of the galaxy microwave background will look like this. If this is a Goldilocks universe, it's just flat, just the right amount of matter and energy to make the universe flat, then I'll produce a pattern like this. And if the universe is open, I'll produce a pattern like that. And if you actually paid attention when I showed you that curve, this is the pattern you saw, and even the color scale you saw. So then you start doing numbers and do fitting, and you see that's how we can get to the 1% level in terms of curvature. Right? So it's going back to this spectrum. The prediction is if the universe is flat, this should peak at 0.9 degrees. And the universe is pretty flat. And these guys should be, half of that and a third of that. So you can sort of measure. In fact, there's many things, so I can show you this, how powerful the spectrum is. So curvature, the curvature of space, as I change the curvature of space, it just moves the peak left or right. All I have to do is measure the locations of the peak. I measure the geometry, not the topology, the geometry of the universe very precisely. Okay? Put the dark energy in, it doesn't show up very strongly here. It shows up in second order and other things. But if I change the amount of matter, all the peaks go up. If I increase the amount of matter, right, all the peaks go up. And they go down if I decrease the amount of matter. So I just look and see the heights of the peaks. Right? But here's another thing that's very interesting. The ordinary matter, which we science call baryons for historical reasons, and astronomers don't call it that. The first peak goes up when you have baryons, the second peak goes down. The third peak goes up, the fourth peak goes down. Here, all matter, right, dark matter makes everything go up. Here, baryons make every other one go up, and then the odd ones go up, and the even ones go down. So if I measure these peaks very precisely, which I've shown you the current data, or nearly the current data, right, I measure these peaks very precisely, and I notice the second peak is down a little bit compared to where the third peak is, but not much. I can tell you that 4% of the universe is made out of baryons. And I can tell you that 27% or so is made out of matter. Right? So 27 minus 4 is 23. So I can tell you, I can separate the two out. Right? So this is the power spectrum stuff. The great discovery was when people were looking at the sun, they started seeing lines of elements, and they realized it was helium and hydrogen and so forth. They could tell that this remote object, 150 million kilometers away, they could tell what it was made of by looking at the lines and comparing it to the same elements on the Earth. Now we routinely look at stars that are billions of light years away and determine what elements are in them, right? And we use those same lines to tell us how rapidly the universe is expanding as it gets stretched. But often, like calcium has an H and a K line that have a certain spacing, and you just see that line migrate across the sky as you look further out in the universe. So spectral studies are very powerful ways to learn about the universe. So here we're using an angular spectrum of objects whose size we know. And so the only question is, how do we know the size? And that turns out to be also very simple. So it's how far sound can travel from the beginning of the universe until the universe gets to be 1,000 times smaller than this. So what is the speed of sound in the early universe? So this turns out to be very simple. If you studied your freshman physics, the speed of sound is equal to the mean speed of the particles that are carrying the sound, in this case air molecules, divided by the square root of the number of dimensions you live in, which happens to be 3. So it's the square root of 3. What are the particles in the early universe? And the early universe is dominated by light. So it's the speed of light divided by the square root of 3. So it's roughly 60% of the speed of light. So I can tell you it's 400,000, a little under 400,000 years. So 400,000 years times the speed of light divided by the square root of 3 is how big this object is. It's going to be the brightest set of spots on the sky. And then I know the age of the universe, I can solve all this problem. I can figure out the distances and the times. And then I can predict where this peak should be in Euclidean geometry, or if I slightly vary positive negative curvature. And it's very simple. And that argument I gave you is good to 5%. Right? Certainly good to better than 10%. And then we're getting so good now, we actually have to take second order effects into account. There's a little bit of loading because of the matter as the universe expands. The fraction of the particles that become matter becomes more important in terms of total energy. But also it does matter what the particles are, whether they're dark matter particles, whether it's the dark energy or whatever else. And there are slight corrections that are about the 5% level. We're already doing that. But we have cross checks because we have more than one set of data points. We don't just have one number, one observation. We have hundreds of data points here. And we're just solving for a few numbers. So we're able to show that the universe is very close to flat. Yeah.
Dr. John?
I have a question. One question, you mentioned that end of this month or next month, our plant surveyors will be launched. Now, let's hope it will be launched and working properly. Now,
we hope that it will be launched, and we certainly hope it will be working properly.
yeah.
It's going to go through this vibration.
Yeah, not like the carbon observatory, the recent one. Now, now it's at higher resolution of the intensity and the polarization. Now, with a higher resolution of the intensity of polarization, you can do it. Is there any, you are measuring at higher resolution, is there any new discovery you can make from it? Or just at a more greater decimal point?
Right. So when we were proposing it, it seems now a long time ago, but it was not so long after the original discoveries, everybody was saying, well, we can do the first few things that were on our list. Of course, we've done them now. And including discovering these acoustic peaks and seeing the stuff and figuring out what the fractions of things are. And I said, no, we should be, I kept trying to caution people saying, what we should realize is the field have moved on, and what we're trying to do is a precision experiment, the definitive experiment, which truly mapping the early universe as well as we can do in terms of temperature, and do a decent job in terms of polarization. And that's what we end up needing to do. The same thing happened with WMAP, is that it was finding the acoustic peaks was this thing. We actually, from ground-based and balloon-borne experiments, got the first tenth of the first peak. And what WMAP has done is allow us to measure very precisely the first and the second peak. And now ground-based things now. So, when science is really exciting, people struggle and find ways to try and do it and try and beat the schedules. And so Planck, I expect, primarily will actually be revolutionary in the sense that it ties things down so tightly that you actually move the theory forward because you have such tight constraints. That I believe is the main goal. The secondary thing was to create such a large community in Europe of doing cosmology. But there is still the potential for discovery. And the one that I mentioned briefly, one of the things that I think is a great chance for discovery, to me that's one of the most exciting ones, is that when you measure the polarization, you expect there to be polarization at roughly the 5% level of the anisotropies. Those anisotropies are predominantly caused by the energy density variations in the early universe, which mostly are matter, and in the end, matter variations, matter and energy equivalent. But there is, I mentioned there would be a pattern of polarization that could show up, which was a pattern that's predicted not from the energy density variation, but from the fact that you stretch the fabric of space-time when you're creating the universe. So you have two things. You have the energy driving inflation, and that's what is probably dominating the fluctuations we see in the temperature, but there also should be actual, just like I said, the carpet has ripples in it. The carpet of space-time will have some small ripples in it, both in space and time. Some of them will, you can then subdivide that up into a part. It's the scalar part. It's like energy. Energy is a scalar. It's a single. It only depends on location. Or a vector part, which has a direction. Or a tensor part, which we now, when they become free to propagate, we call them gravity waves. That is, there are ripples in space-time that move along with the speed of light. So when the universe is made, you cannot make it perfectly. Quantum mechanics causes there to be small variations. There must be at some level small variations, small ripples in the fabric of space-time, and some of them will show up as gravity waves. And the gravity waves have both a polarization and the direction of propagation. So they have two directions they can pick out, whereas energy density variations only have an intensity. So the pattern you get for polarization around a energy density fluctuation is either radial or tangential polarization, whereas you can get, I have the UV modes for another thing here. Let me see if I can get down to here. Vorticity or shear to the vorticity. So this is the pattern. Can you see the difference? See how there's a flow around this direction? There's a direction that goes that way. But when it's the mode from just energy density variation, it looks like that. You can't tell whether it's flowing right or left. But here you can definitely tell. Okay. This pattern is an indication that there are gravity waves. That's an indication of the tooling marks from making the universe. When you made the universe, you cannot make it perfectly. It's made of, not of atoms, but it's made of stuff that quantum mechanics fluctuate. The fabric of space-time itself must fluctuate. That's why general relativity eventually gets in trouble with quantum mechanics. But here we're talking about the quantum universe. You can write a wave function for the universe when it's really tiny. This is going to be important. That wave function still must exist now. That's a nice problem for physics to try and solve for that wave function.
My second question is, you showed, wanted to show earlier the animation on the clustering of the dark matter. So as time passed by, the dark matter clustered more and more. Are these just arbitrary simulation or actually from your WMAP information and COVID information, you actually knowing how much dark matter is there, and as time passed by, is how they cluster.
Right. So we know how much dark matter there is fairly well from our fittings. However, we don't know the fluctuation power spectrum, all the smallest scales, the scale size of galaxies, because so far, even with the better beams with WMAP, you only get down to cluster size, the galaxy cluster size. With COBE, it's only the supercluster size that we actually measure down to. It's very coarse. Right? Like I say, we're measuring the continents and small islands like Australia or something. That's about the scale size we're at. And so what you do is you see that power spectrum. You think about what that means about what's putting there a fraction of a second, and then you evolve it through the sound wave period. So sound waves actually dissipate a little energy. So something on the size of our galaxy, it actually started with as a bigger fluctuation, and only about 5% of that fluctuation survived to make our galaxy. So smaller scale things the more it dissipates. The large scale things like clusters of galaxy, they pretty much didn't dissipate, they just clumped and formed. And so we put in a simple form and a simple transfer function, and you run that simulation. I can find the simulation in the place and run it for you if you'd like to see it. And so, but now we're measuring on finer and finer scale. With Planck, we'll get to an even finer scale, and we'll test that. But we have a good idea how it could be, and now we're only looking for slight tilts and bends or whatever it is in that spectrum, which again would be a hint about what's going on in inflation. You think there should be no scale picked out. It should be essentially scale free. Right? And that's a simple power law or no dependence on size at all. As if inflation was going on for a very, very long time and not changing, it would give equal size amplitude on average to all the fluctuations. And we're close to that. But now we're getting so precise, we think that the tilt should be essentially 1/100th of a change in the amplitude per decade that you go in physical size, right? And we're looking for really small things, but we can look over many decades, and so we can test to see, because we think inflation must eventually have to turn off, so there has to be a slight tilt to it. so it can shut off, so the universe can start slowing down, and structures can form. So we're trying to understand these phenomena and in a much deeper way. We can put in a simple model for inflation and have it just shut off automatically, and then you can work out what happens. When they do those simulations, they just do that analytically, put that power spectrum in, the transfer function through the oscillations, although we do have multiple codes that we can run, and they run very fast now. We have tried to do simulations of 10 different parameters, right? And so you can divide 10 different parameters in 10 sections, you have 10 to the 10th possible simulations. So you got to get the simulations to work very fast in order to do a larger number of them. And so there's a lot of work to be done, right? I mean, it takes thousands of processors some time to do that. We do it stepwise, but we have good reasons to understand what it is. But a full-up long-term simulation, we're going to have to determine, like with Planck, the parameters of the universe very well. And once we have those parameters, then we can take a narrow region, right? So only 3 steps or something in 6 or 7 different parameters. So it's just 3 to the 6 or some number of simulations we have to run. So we can maybe afford to do that, right? Even with Moore's law, though, that's the kind of thing. But you kind of know roughly the right regime you're in. You're still cross-checking to make sure there's something you haven't missed or there's some other window. And so you do a larger sample right now. So you do it piecewise in terms of what's happening. But there are a lot of exciting kind of things that you can do. There's a lot of work left to do in the field. We've made tremendous progress. Just sometimes I get upset because my colleagues say there's 95% of the universe we know nothing about. Right? But the fact is we know a lot about the properties of dark matter and the properties of dark energy. We just don't know what it is yet. We haven't seen it. We haven't felt it. We can't write equations down except the simplest possible models. So sort of equivalent to ideal gas law without actually having a model that their molecules bouncing together and statistically it comes out right. And so we haven't made the transition from macroscopic physics to microscopic physics. But we're well along the way, and that's what I think the goal is for the next couple of decades.
Okay. I'll just pose some questions. As a moderator, I'm not just asking basic questions. One is what comes before Big Bang, which you know is singularity, and then how does Big Bang occur in order not to violate the cosmological principle about homogeneity isotropic. And the third question is what SNAP will do to prove that the existence of dark energy.
Okay, so let me go with the easiest one, which is the last one. It's no longer called SNAP, even though that's what, when we were proposing it and we were working on it and putting up a possible mission that could be done, we called it SNAP because it was a kind of a cool name. And now it's called something a little less cool, JDIM, which stands for Joint Dark Energy Mission. Right? It hasn't got the connotation of SNAP, but in the end, you rename it after some famous scientist. So it's not the end of the world. So right now, SNAP is in the midst of a partial, not SNAP, JDIM is in partial reorganization. It will be a joint mission between DOE, which started it, although now it's a small partner, NASA, which you just thought was a great thing and took it over, and now the European Space Agency, which is very recently joined, and they're still figuring it out. They're still trying to work it out and make it an opportunity so scientists can propose from all around the world, but primarily from Europe and North America. And so the goal there is to try and as a primary mission, try and understand the properties of the dark energy or the wave accelerating universe. And there's two primary approaches to that in terms of the way you do the science. The first is you measure the trajectory of the universe. So the analogy I give is if I take this and I throw it up in the air, it will make a nice arc. It will come back to the ground, unless I throw it hard enough and it will escape. But it'll make a nice arc. The universe starts from a very small size. Okay? So just instead of making height, make it size of the universe. That is the height of the universe is the typical distance between galaxies. It'll go up in a sort of a parabola, but it now zooms off. Right? So it has this funny shape. If you measure this trajectory extremely precisely, Just if you measure it, it's exactly a parabola, and you do your elementary physics, you'll realize the force of gravity is constant the whole way. And if it's not exactly a parabola, it goes further, you'll realize the force of gravity goes as 1 over r squared. So if you can measure the trajectory extremely precisely, you can measure the net force. So you can go from the kinematics to the dynamics. So that's one approach. It's just measure the kinematics of the universe extremely precisely and infer the dynamics. The other is the thing that I mentioned. When the universe starts accelerating, the formation of structure, and the formation of things that would be larger than what we call a supercluster now, will be cut off because its gravity is trying to pull matter in, and the expansive universe is pulling it out. But as the universe speeds up, then the things that were just barely getting pulled in will no longer get pulled in, they get pulled apart. And so if you study the very largest objects carefully, or if you study what we call the curve of growth, that is how quickly objects form as a function of the size of the objects, you will then see when dark energy comes in and how it affects. So there's 2 different ways. So how do we study those? Well, one is you have standard candles or standard rulers, right? So a standard candle is a supernova of a fixed brightness, so supernova of fixed brightness. Another thing is the baryon acoustic oscillations. Those bumps, those sound waves I showed you in the early universe, if you really wanted to, I can show you a nice little simulation of this. If you make a little lump in the early universe, the little lump does a funny thing. The center part of the lump stays there, but a spherical shell goes out, and a spherical shell eventually becomes a size which, when the universe is expanded to the size, is 500 million light years across. So this is very strange. How does this happen? Well, when you then realize the universe is a 5-component fluid in the early universe, it's almost a perfect fluid, the dark matter stays in the lump. The light interacts with the ordinary matter very strongly and pushes it out, just like the sun is pushed out, puffed up by the light. So the sphere that expands out around the dark matter is ordinary matter, right? And that's the object we see that looks at 9/10 of a degree in this universe. And then what happens in the simulation, you see once the light separates from the radiation is free to separate from the matter starts falling back in the gravity exponential well of that. But there's a little ring, a sphere, a spherical shell, out at 500 million light years that don't fall in, they just make a few percent extra galaxies, right? And so, actually I can go back and show you a picture of that, I think. Oops, I'm going the wrong way here. Let me see. I thought it was, no, it is earlier. So anyway, this has actually been observed now. If you look around really big clumps, okay, I can do you the simulation, I hope. Here's a single lump, and it makes a nice Gaussian shape in the early universe. And if I click on it, it works. It should work. No, I guess I can't make it work for you. So here is it in 1 dimensional instead of 2 dimensions out of 3. And you see the universe is made of dark matter, ordinary matter, which is called gas, photons and neutrinos, and it's also gravity waves. And when I let this go, you will see this lump, at least if it works. I'm getting this to do in reverse order, it doesn't always work. Well, it almost shows. What you see is it separates out, and you see this lump, and this very thing that shows up as this big peak in the cosmic microwave background shows up as a little peak of galaxies out here. And these are the data points. These black things are data points. These curves are various models depending upon how much matter you put in the universe, for example. And so there's now been 2 experiments. This limited sky survey in the 2-degree field of view, and now this limited luminous red galaxies that show this little bump out there. So that standard ruler, that's the standard ruler we measure the geometry of the universe. It also allows us to measure distances to objects very precisely. And we can measure the redshift, so we can measure the scale size of the universe as a function of time, very precisely. So we have supernova, we have the baryon acoustic oscillations as probes. So you want to do those on your satellite. Although we think we can do this from the ground, so we're starting up a big experiment to survey billions of galaxies out over a large volume, right? So it wasn't, we got automated completely, got a big computer run, lots of capacities. To make this map, to make a map of a lot of the sky where galaxies are, and look at them very carefully in 3 dimensions to see these spheres around these clusters of galaxies. And then we will be able to see how things are behaving, right? And you have to do a very large survey because there's a little tiny bump on this map of the universe. When you look at this longitudinal sky survey, it's an object that's 500 billion light years across, right? The typical void is 50 billion light years across. So it's going to be 10 voids across. Right? So you need a very huge survey of the sky. That's why you need to sample millions of galaxies over a large thing and make it very, very precise measurement. So we have a design where we're going to be able to take the redshift of 6,000 galaxies, or at least 4,000 galaxies at a time. So you have a field of view that's 3 degrees. You pick out 6,000 galaxies there, and you measure their redshift very precisely. So that's the part of the thing. So this experiment is called POS, and the big version of this is called Big POS. In English, is funnier. So this is one of the objects that you can look for, and then the curve of growth is another object you can look for, and then you can start doing these kind of measurements where you use the cosmic background to tell you the universe is close to flat. You use supernova to tell you the universe is accelerating, and you use variant acoustic oscillations to constrain it. So this is how much energy is in matter. This is how much energy is in dark energy, and we find there's an intersection where you can do it precisely. And then you can even look for, is this fraction, is the kind of energy changing? Is this pressure? It's equation of state. Right? So you have an ordinary, like an ideal gas, you have an equation of state. This is the ideal gas law. This, whatever this is, there's some equation of state. -1 is what you would get for the cosmological constant or vacuum energy. So far, the data are agreeing with -1. This is one of the things we're trying to do is this really the cosmological constant, and are we doomed to an accelerating universe, or is it slightly different? And it has to be near -1, both for observations and for the fact the universe is as old and big as it is. But the question is it exactly -1? Is it different? And the future depends on that. If it really is the cosmological constant or vacuum energy, you're all going to die. It's life or death for all living beings, not just you. And so it's a big deal. So that was the easy question. So when you can ask questions like this and get precise answers, then it's important. And the question of whether you're all going to die or not, that's also big. So now you're asking, what happened before the Big Bang? And the answer is, we don't know. And but we have several different theories that are still consistent with our observations. One of those is there was nothing before the Big Bang, literally nothing. Right? The universe popped out of nothingness, not even a vacuum. The vacuum is complicated and has a lot of properties, but truly nothingness. And those of you that know quantum mechanics knows if you have a vacuum and you take out you've taken out all the matter and all the radiation, there's still a complex structure in there. And quantum mechanics tell you virtual particle pairs appear and disappear, annihilate. And on average, they're there for a short time, but on average, they're not there, and it averages out to give you the properties of the vacuum. It is possible for the universe, or the universe plus an anti-universe, but it doesn't matter if you do it right. The universe can give you its own antiparticle. And you can just pop the universe out of nothing, as long as the universe has the same quantum numbers as nothing. And so one of those quantum numbers that's extremely important is the total energy. But a universe that's flat has 0 total energy. So we're actually very close to the situation which we know we have to have if the universe started with a very small amount of energy, or 0 energy, this came from nothing, then we're actually not far from that. But just the fact that the universe is going to be so big almost automatically forces you to have a net energy in the universe be close to 0 and reasonable scales. So that's one possibility. Another possibility is that the beginning was very complicated, tangled up like spaghetti, and time goes in all different directions. So before, it doesn't have a clear definition because it's like you're at the North Pole and you're asking which way is north. And, well, it's that way and that way and that way. If I keep walking, I always end up going south. Right? Doesn't matter which way north is. And you can make a universe in which it's equivalent to a North Pole without rotation. So it's actually any point on the universe is equivalent to any other point. And you can actually make where the beginning of time is arbitrary. Because it's just like what point on the surface of the sphere is the beginning of the sphere and what point is the end of the sphere. It's just by definition, because they're all. You can make universes like that And a universe that has accelerating expansion is very close to that, perfect speed. So that's one possibility. Another model is you have a situation in which the thing you call the universe is inflating, accelerating like crazy, and it grows exponentially. So it gets big, and then it gets really big, and then it gets super big, and then you get exponentially bigger than that. And then some little tiny small part of it has a quantum mechanical fluctuation that allows it to trigger and go into normal space. And the entire thing that we call the universe, everything we can see in 14 billion years in any direction, plus a lot further, is only just a little teeny speck. And what is a humongous volume, it is all accelerating. And we just have to be, we think we're in the universe, and we're just this part that just kind of took a vacation at the beaches in Malaysia. Right? And but if we were able to get back to the beginning of the Big Bang, we would see things going whoosh, that is doubling every 10 to the minus 35 seconds. Nanoseconds are like forever, like double, 10 to the 20 times. It's tremendous inflation. And so in that situation, what's before the Big Bang is what it all has that's the interesting, you can make a model of that, it's called eternal inflation. It's always been going on, it always will be going on. It's kind of emotionally satisfying because of eternity. But it's not of relevance to us because we live in a special place. We live in a place that's very big, and our place in that place is very special. But it's unusual compared to the rest of it, even though it's incredibly large. You feel better now?
Yeah.
More significant. So it's very funny. I don't know if you ever.
No, because that's what most of my students ask when I talk about cosmology to students.
So did you ever?
I have the answer that when you are in North Pole, you're asking where's North.
Right. Well, I mean, there's different versions of that.
Yeah.
But it's easy. If students have any math, it's very easy to show that in the case where you have the accelerating universe, that you can actually move where the origin is, and there's nothing special about where you think the beginning of time is. It's just an arbitrary. It's just where you have to pick your coordinate system. It's not a true singularity or a true beginning. It's just a coordinate convention. So the thing that this is supposed to remind you of, if you ever read that was his last name, with the Hitchhiker's Guide to the Universe, and he's got the president of the galaxy gets put into the total perspective vortex, and this is what they do as ultimate punishment to people who are really bad, is they show them their net worth in the universe. So they put them in this thing, the machine, which gives them a total perspective of everything, right, and their place in the universe. And it drives everyone mad because they're so totally insignificant. So this is not supposed to be the total perspective vortex. This is supposed to be a little perspective vortex. But it should make you think that peace is probably a good thing to do because, a lot of the little wars are kind of petty.
Okay. I think we are running out of time. Just sum up, please. We can talk later because we're running out of time. I just got the cue from the organizer. I have to sum up. First of all, I would like to thank Professor Josh Fitzgerald Smoot for his very enlightening talk, as well as fielding all the questions with all the answers prepared on slides. Even though unfortunately we can't get some of the simulation, but we have some ideas for it. What is most important to us now is that what Professor Josh Fitzgerald Smoot has done was, after going through Kobe, and it goes into the second generation Wilkinson microwave anisotropy probe, and then now it's moving on to the Planck probe. And if I make to understand that in the Planck mission, there is supposed to be the HEMT, which is high electron mobility transistors, to do some measurement on the anisotropy and the irregularities of aberration. So with that, I would like to once again thank all the distinguished guests, honorable guests, as well as those who are here. And we would like to give our strong appreciation to Professor Josh Fitzgerald. I would like to give the floor back to the Master of Ceremony, Mr. Pyros.
For an interesting and insightful dialogue and Prof. Zamri for moderating the dialogue. Ladies and gentlemen, we would like now to call upon yang berbahagia Puan Alina Ahmad to present a memento of appreciation to Professor Smoot on behalf of National Space Agency of Malaysia. Thank you, Puan Azrina. Ladies and gentlemen, now we would like to call upon yang berbahagia Dato' IR Dr. Yadi Ahmad Laiden to present a memento of appreciation to Prof. Smoot, followed by Prof. Zamri on behalf of Academy of Science Malaysia.
Thank you so much. It's beautiful. That t-shirt for Team Thursdays. Yes. So thank you so very much.
Now against Dato' on behalf of National Academy of Science of Malaysia to give a special memento to Prof. Zamri. With that, ladies and gentlemen, we have come to the end of this dialogue and hope you have benefited much from the discussion and sharing of ideas. Everyone is cordially invited for refreshment at the VIP lobby of this building.